In solving many of our optimization problems that are constrained, or perhaps unconstrained, where we just let the constraint function be 0 equals 0, which is always a true statement, we obtain a value of lambda in solving our two equations. Now, as just a recap, in order to solve an optimization problem that is constrained, we are looking for where the gradient is some multiple of the gradient of the constraint function. And the way we've interpreted that is the gradient vector always points perpendicular to the contour, and when g and f are tangent to one another at this one point right here, the gradient vectors of both functions, they may point in opposite directions, but they are parallel to one another. So the gradient of f is parallel to the gradient of g. And this point right here that we find as a result of that point is what we would refer to as x sub 0, y sub 0. The subscripts are there just to denote that there are some fixed values of x and y. Remember, x is a variable, y is a variable, x naught is a specific value of x, and y naught is a specific value of y. So what we need to in general do is we solve this, which if we have a three-dimensional function, this consists of vectors that have two components each. If it's a three input, one output problem or a four variable problem, then we'd end up with three equations coming out of this. So this is one vector equation which actually forms individual scalar equations. And then we also need to ensure that g of x, y is equal to some constant c. In the case where this is an unconstrained function, this right here would be 0 equals 0, and so we could solve unconstrained problems as well. So we're solving this system of equations right here. Now, the value that we get is we end up with three values. We end up with what we want, which is x and y, but we also get in the process a value of lambda, which up until this point we've been ignoring. Now, the mathematical derivation is a little bit interesting, how we get at what the physical interpretation or the geometric interpretation of this value is. Let's first of all start with some quantities. So we can look at the partial derivative of f with respect to c. In other words, how does the output of the objective function change when we change the value of c by 1 unit? So c is the value of the constraint. This could be a budget. And maybe f represents our profit. So if this were to be profit or dollars of profit, and this value of c was to represent how much we could spend on manufacturing, then this might be dollars of budget. So the way we could interpret a number that would come out of this is how much does your profit increase by, or potentially decrease by in certain situations, if you increased your budget by $1? Well, in this case, we'd probably expect that to be a positive because the more you could spend on manufacturing, advertising, etc., would probably have a positive impact upon your profit. Now I'm going to make this argument. There's also a quantity here that we could represent that we would say dx naught dc. Okay, what would be the meaning of this value? Well, this would say if you increased your budget by $1, how would that affect the x value of your optimal point? So maybe if x and y represent how many units we could produce, if you increased your budget by $1, then the number of units of x that you could produce would probably increase. Now I also have this quantity, the similar quantity. How would the number of units I could produce change if I increased my budget by $1? All right, well, if I put an equal sign here, I clearly see that, okay, the units are not the same because this is units divided by dollars, this is dollars divided by dollars. But if I wanted this to have units of df/dc, I could apply the chain rule, and I can say, well, I really want this x naught to cancel out. And so that would cancel out my x naughts, and in order to have df in the numerator, I would have to multiply df dx naught by dx naught dc. So this first factor here would be, how does your profit change if you increase the number of units you end up manufacturing? Cool. All right, so that has a good interpretation. We could do the same thing here. We want to add these together to use the chain rule to end up with df/dc plus df/dc. So I'd have to cancel out the dy naught, and I'd have to introduce a df here, and we see that the units cancel out, and we get df/dc plus df/dc. The second df/dc is how your profit would change due to an increase in the number of optimal units you produce. Okay, well, how is this getting at giving us a sense of lambda? Well, at this point, we're going to make an observation that comes back to equation 1 here. From equation 1, we know that df dx is going to equal lambda times dg dx. And I know that because that's what the gradient vector contains in its top component, df dx. That's df dx. This is df dy. And over on this other side, this is the gradient of g, so this would be df dg. And, sorry, dg dx. dg dx. And this here would be dg dy. So by equality, df dx is lambda times the top component, and that gives me this equation here. And then the bottom component says that df dy is equal to lambda times dg dy. I'm going to use that, and I'm going to just do a substitution in here. So this equals, well, we just said that df dx is going to equal dg dx. But I am going to, actually back here, we don't really need this dx naught, because x naught and x represent the same variable. And you'll see in a moment how this all pans out. So df dx is lambda times dg dx. I'm just making a substitution for this piece here. So multiplied by dx naught dc plus df dy is going to get replaced by lambda times dg dy times dy naught dc. And now I observe that I can factor out a lambda. So I'll factor out a lambda from both of these terms. I'll have dg dx times dx naught dc, and then plus dg dy times dy naught dc. All right, well, this quantity in the parentheses, I see that by the chain rule, that the units that cancel out here actually lead me to the conclusion that this is dg dc. So I get lambda times the thing in the quantity represents the derivative of g with respect to c. And by equality, and this is just purely algebraic stuff at this point, df dc is equal to lambda times dg dc. Now this might look all too familiar like equation 1, and it really is, but notice that my differential in the denominator is with respect to c. Now if I do a cool little thing here and I divide both sides by dg dc to cancel it out from the right-hand side, so these cancel, and I divide by dg dc over here, now something really interesting happens. The dc's cancel, and what I end up with is lambda is equal to df divided by dg. Okay, what does this mean? Interesting. So at least I know the units of lambda, and in my situation up here that I'm illustrating, this would represent the change in profit change in profit per unit change in the value of the constraint. So what I could say here is, in this context, well, let's go ahead and take a look at an example. But if we increase, basically, if we increase the constraint by 1 unit, we increase the constraint by 1 unit, lambda is the amount by which we expect our objective function, which is f, to change by. Okay, let's take a look at an example. Here we say that the quantity of goods produced according to the function f of xy equals this is maximized subject to the budget constraint that x plus y is less than or equal to 3.78. The budget is increased to allow for a small increase in production. Okay, so now we're going to say, well, what if we increased this by 1 unit? What effect would that have on our objective? Well, one thing we could do is we could resolve the whole system, but what we're really trying to do here is take advantage of the value of lambda that pops out of all of this. We want to be able to interpret that lambda without having to do way more work. We just want kind of a sense of what it tells us. What is the price of the product if the sale of the additional goods covers the budget increase? What is the price of the product if the sale of the additional goods covers the budget increase? Okay, so we solved the equation. So this is the partial with respect to f of f with respect to x equals lambda times the partial derivative of this with respect to x, which is going to just equal 1. So this is really lambda times 1. Now we take the derivative of this with respect to y, that's this guy here, equals lambda times the derivative of g with respect to y. Well, that's going to be 0. The derivative of y is 1, so we get lambda times 1. And then there's our budget constraint. This is what we would call number 1 up top. This right here is equation, or the second portion of our system of equations. And now we solve, we find out that x equals 2.52, y is 1.76, and we find out that the maximized budget is 2. Now that could be in hundreds or thousands of dollars. We'll just leave it as 2 units of our profit. Now we also get the value of lambda. If we solved using Wolfram alpha, we get 0.53. Well, we just said that lambda is going to have the units of df dg. Okay, so in our case, f represents, maybe we'll say it's hundreds of dollars, but we know that this value is equal to 0.53. And I'm going to put it over 1. That way I could compare this as a unit rate. So 0.53, we'll just say this is hundreds of dollars. And we know that G is related to our budget, so we'll just say that this is per $1 of budget. So how do we interpret this? Well, we could say that if we increase our budget from 3.78, again, this could be, we'll just say this is hundreds of dollars, $100 of budget, from $3.7800 or $378, we'll leave it as 378, to, well, it's to 4.78, so that's going to be to $478. We would expect this value, we would expect our maximum profit of 2. We expect our profit of $200 right? Because 2, we're just saying that our profit in this case is in hundreds of dollars, should increase. We expect our profit of $200 to increase. Well, we expect it to increase by $0.5300 for every $100 of budget. So if we increase our budget by 100, we expect our profit to increase well, 0.5300 is $53. So that means we should get an extra $53 of profit. So if we increase our budget from $378 to $478, we expect our profit of $200 to increase to $253. And this ratio here is of the utmost importance. It tells us what would happen hypothetically if we were to increase our budget constraint. We didn't need to do any extra work for this. That value comes with solving the system of equations, and it has this really cool interpretation. Now remember, this is an instantaneous rate of change. So if we actually increased our budget by 1 unit, which is $100, then we would expect our profit to increase by roughly $53, though again, that's an instantaneous rate of change. It just gives us the sense of, does it even make sense to consider trying to increase our budget? If we found out that this was a negative value, in some cases, by increasing your budget, maybe you're just throwing more money into the system, but you don't have enough workers to be able to do the extra production, so maybe you're actually losing money by injecting more into the budget. So if lambda came out to be negative, we know that it wouldn't even make sense to try to increase our budget. But in this case, it seems like if we could possibly make more money.